Greetings, my name is Nareddy Kumar Reddy. Today we will be presenting our paper titled An Ensemble of Proximal Networks for Sparse Coding. I would like to thank my co-authors in aiding me in writing this paper. The authors of the paper are as follows: Kartheek Reddy, Swapnil Mache, Praveen Pokala, and Chandra Sekhar. We are from University of Science, Bangalore. We would like to thank Prime Minister's Research Fellowship for aiding us in conducting this research. We begin with the basics of compressed sensing. Compressed sensing is a methodology where we compress lengthy sparse vectors into small number of observations, and this is achieved with the help of linear transformation. So on whole, this is a undetermined system of equations, and hence it is ill-posed. The applications of compressed sensing can be found in many computational imaging and image restoration tasks. How do we recover the sparse vector X given the sensing matrix or linear transformation matrix A and observations Y? We can do so by minimizing the number of non-zero values in the recovery vector, and the recovery vector has to conform with the observations via linear transformation. Whereas this problem is computationally intractable and it requires exhaustive search. So for practical purposes, this problem can be relaxed into a convex program, that is minimizing the one norm of the recovery vector, and at the same time we allow for some noise to creep in the observations. So we would be minimizing L2 loss of y minus ax along with L1 norm of the recovery vector, and this L1 norm promotes sparsity, and that can be replaced with a general sparsity promoting penalty, so which can be convex or non-convex. Let's look at the convex and non-convex penalties that we have readily available. So in this paper we will be considering L1 norm as a convex penalty and the minimax concave penalty and smoothly clipped absolute deviation penalty as both non-convex penalties. The advantage with these penalties are they have closed form penalty function, at the same time they also have closed form proximal operator. This leads to more practical algorithms which can be implemented at ease. Let's look at how these penalties looks like. So as you can see, the dotted blue line is nothing but the L1 norm. You can see that the penalty increases as it goes to higher amplitudes, whereas the non-convex penalties such as MCP and SCAD, they settle to a certain value at the higher amplitudes that results in lesser penalty for larger amplitudes. So that can be seen, the result of that can be seen in the proximal operators, where at larger amplitudes the proximal operators of MCP and SCAD are not having any bias, whereas L1 penalty is having certain bias. That results in recovery of larger amplitudes in much better fashion using non-convex penalties. But also non-convex penalties have higher variance compared to the L1 norm. That is the reason we would like to consider all three penalties in our formulation. Now let's look at the optimization of the convex program that we have seen earlier. So this can be solved using iterative soft thresholding algorithm, and as part of this algorithm we would be doing gradient step and we would be doing at the proximal operator step. And in 2010's work, Jan Lekun and Gregor have proposed a learnable iterative soft thresholding algorithm based network, that is, using deep learning we can come up with a learnable transformation and proximal operator. The proximal operator stays the same, but the threshold parameter is learnable. At the same time, the linear transformation, which was fixed gradient in the IE star, will be learned completely using the neural network. And as we have seen earlier, since the proximal operator hasn't changed, the whatever the limitations which are there with the soft thresholding will be carried over to learned star. As we have seen how learned ISTA derived from ISTA, the MCP and SCAD, they will have corresponding networks with non-convex proximal operator as their activations. In this work, we would like to use an ensemble of those proximal networks to achieve better sparse recovery. As we can see, suppose this is Lista, this corresponds to the MCP network, this corresponds to SCAD network, and all these learnable linear transformations were independent, and the proximal operators are independent. And at the end, we will take an ensemble of the outputs, and this would be our recovered sparse vector. We also propose a shared weights ensemble network where we would like to minimize the number of parameters that we are learning. So, as we can see, all these networks have similar linear transformations, and we can share the weights between them. In that case, only proximal operators are going to be coming from different networks. In that case, this is called EPNet shared, and this one is called EPNet unshared. The advantage with the EPNet shared is it is having roughly as many parameters as the original networks, whereas the EPNet unshared is having almost 3 times more parameters than the individual networks. We also would like to show that the EPNet shared, where the network weights are shared among the ensemble, results in a deep unfolding network, which corresponds to a composite regularization problem. That results in a stronger back for the proposed EPNet shared because deep unfolding networks are reliable, understandable, and interpretable. Now we will look at the simulation results. We compared our method with fast iterative subthresholding algorithm VISTA, learned AMP algorithm, and learned ISTA algorithm with coupling, and LISTA algorithm, and SCADNet and the MCPNet. So the experiment details are as follows. We would like to retrieve a 150 dimensional vector from 100 dimensional observations. The sensory matrix is generated from a random Gaussian distribution. And we varied noise levels from with standard deviation 0.01 to 0.1. In this table, all the numbers are given in dB. As we can see, in all the noise levels, the EPNet shared and EPNet unshared are performing better than the competitive methods. Moreover, EPNet unshared is having a large margin over the other methods. And despite having same number of parameters as the other methods, the EPNet shared is still having a margin of improvement over the competitive methods. This graph shows the variance of the performance with a change in the sparsity factor rho. So this corresponds to 10% of this non-zero values in recovery vector, and this corresponds to 25% of the non-zero values in recovery vector. And we compare Lista and MCP network formnet and EPNet shared. As we can see, EPNet shared is having consistent improvement over the other two compared. And as we can see, there is a huge margin between Lista and the Ensemble network and formnet. And this graph corresponds to low noise and moderately high noise. Now we look at the PES performance. PES means probability of error in support. So an error of 1 means that it is having huge difference in the support of ground truth vector and the recovered vector. And the error of 0 means the supports of recovered vector and the ground truth vector are very close by. As we can see, EPNet shared is having huge number of dot pixels that corresponds to lower PES values. The lower the PES, the better. You can see that EPNet shared is the best among the four. The MCP network comes closely second. Now we will move over to image denoising experiments. We'll be using set11 datasets and BSA68 datasets. For image denoising, we will be considering convolutional networks based on the proximal operators. As baseline, we took convolutional lista, which is convolutional counterpart of the lista, and conformnet, convolutional SCAD and CORNET. CORNET is a composed regularized network appeared in ICIP 2020. As we can see, across both noise levels, the proposed methods are outperforming the computer methods. And these results corresponds to basis 68 dataset. Now we will analyze the learned ensemble proximal operator. This operator has been shown in magenta color. When we compare it against sub-threshold, we can see at higher amplitudes there is a less bias with the ensemble proximal threshold operator, and it is having lower variance when we compare with the MCP threshold because of its smooth contours. Now let's look at the image denoising example where the convolutional lista is more closer to the noisy image, whereas the convolutional loopnet is more closer to the true image in both contrast and the noise. Now we look at the violin plots of the learned distributions of the L1 penalty, MCP penalty and SCAD penalty weights. As we can see, MCP penalty is taking larger weights, that means it is contributing more towards the ensemble proximal operator. And also when we compare between L1 and MCP, we can see MCP is slightly higher than L1, and when we look at L1 and SCAD alone, both of them are nearly contributing same. And when MCP and SCAD were used, in that case MCP is contributing towards the ensemble proximal operator slightly more than SCAD, but we can observe the huge variance in the weights. Now we will conclude with following points. We have proposed EPNet, an ensemble framework with 3 deep unfolded proximal networks, and with the help of the ensemble network, we are able to solve the sparse coding effectively. And we have proposed 2 variants, EPNet shared and EPNet unshared. The EPNet shared, we have shown that it is a deep unfolded network arising from composite regularized formulation. And also an analysis on the weight distribution in ensemble proximal network showed that the MCP penalty received higher weightage than the other 2 penalties in sparse recovery and image denoising tasks. In the current paper, we have shown the benefit of ensemble learning for model-based networks in the context of sparse coding and image denoising. The potential future applications include image restoration and compressed image recovery. We would like to thank IEEE, SPS Society and ICIP for providing us this opportunity.